All right, practical Byzantine fault tolerance. For pBFT to work, we need to make the assumption that less than 1/3 are malicious. With n nodes, we can have a third malicious or late or slow or network failures, but we have to have less than that 1/3. And to reach consensus, we do it in 4 distinct phases. First, a client sends a request to the leader node to invoke service operation. Now, the leader is usually elected or picked at random. There are some things in the article about how to go about picking leaders so that you always have a leader, but basically, you get a request sent to a leader. The leader uses a hearsay system to distribute this request to all the nodes in the network. The nodes execute the request and send the reply back to the leader, and the leader sits there and counts the number of successful replies. When it gets F, which is 1/2 plus 1, it says that this is consensus, and then it distributes that single reply of consensus to all the nodes, at which point it has achieved a consensus state. So the algorithm is actually pretty simple, except for the picking of leaders, and there is a way to do that. There are requirements. The nodes have to be deterministic, and they have to start in the same state. So this deterministic and start in the same state is why all of the nodes in Ethereum use a pure functional data structure, why you can't have outside inputs in the middle of processing, because they all have to be deterministic and they all have to start with the same set of data. And that means that the final result that the nodes get when they've distributed the data will be the same. Now, building a database that has this behavior of deterministic, and start in the same state is hard, and that's also part of the reason why saving data in Ethereum or these other systems that do contracts is expensive, is because this is not a simple thing to get a deterministic database. Part of the solution to determinism is that you can't have any time travel. You can't have a node that runs real fast and then looks at its end result and sees what that end result is before the other nodes get there. So an agreed upon system that works, that produces results at the output that the input can't cheat and see. Now, the leader can be picked in a round robin fashion. You can use some sort of election system to distribute the number of leaders. IOHK's system has a thing called slots, and a leader is picked for each slot, and it's done so that it distributes the amount of leaders evenly over time. And in most proof-of-work models, once the block is agreed upon, that means the signature is made and it is agreed upon, then that is the final block and it is distributed. Now, there's some problems with distribution when multiple different solutions occur and you get uncles. In practice, in Ethereum, we see about 3 of those a year, but it does happen. And the answer is that the Ethereum system has to keep both chains live with the uncles until one of them is longer. And at the point at which it's longer, we have more votes for the longer chain and the other chain is discarded. So you don't have consensus in these things until later sometimes. In Bitcoin, it is 6 blocks, and the blocks are once every 10 minutes. In Ethereum, it is normally 3 blocks, and the blocks are once every 21, 22 seconds. So in about a minute, you can usually reach consensus. Although there have been a few cases where it took up to 6 blocks for it to actually decide on this is the uncle and this is the main one, and you have consensus, which would be about a minute and a half, which is pretty good. Also, with the new version of Ethereum running that uses proof of stake instead, we're talking about 10 to 20 times that speed, which is a few seconds. And with practical Byzantine fault tolerance, this only works well when the consensus is basically got enough nodes that you can reach that F number of F plus 1. So you can't have too small a system. The bigger the system, the harder it is to do that send request to leader and have it distributed to all the nodes. So a bigger system tends to run slower than a smaller system. And that's why we have seen some adaptations where we've proven that just 9 nodes randomly picked is basically sufficient to get us the security. And then when you're distributing to the nodes, you only have to distribute it to that subset. So that's kind of the practical fault tolerance algorithm. It's a lot simpler than the other things. If you want to get into the grungy details of how you pick leaders in different systems, you got to read the paper. Because other than round robin, all of the systems for picking leaders have a lot of steps and a lot of votes as to how you get to a leader, and they're complicated. But a round robin system is a good way to look at how the leaders are picked. And it's got some built-in fault tolerance, as in if a round doesn't happen because a leader dies early on in the process, then it just simply goes to the next one in the next round, and it continues as if nothing had happened. But you have a gap where you lost a cycle. So that's kind of that. Now, I promised I would get back to the $440 million case study at Knight Capital. One day they deployed some software, and the software had a bad combination of things where the old software was not removed and the new software was put in, and the two talked to each other. And the more that the new software saw that the old software said, yes, sell these things, the more the new software sold, and the more the old software saw that it was selling, the more it said, well, because you're selling these things, you must need to continue selling them. And yes, in a matter of, a few minutes, it basically destroyed Knight Capital. They had to have an outside loan of hundreds of millions of dollars. But basically, this was the death of their business in 10 minutes after, I think it was 17 or 18 years that they'd been in business. But if you go searching for this Knight Software and Capital, you can go read about it. This is one of those cases of, if you deploy it and you don't test it beforehand, and it's really, really, really hard to test, that, you get bad results. In cases where I have had systems that I am doing that are online systems, I have actually started the process with injecting basically a proxy that copies everything for a period of time from the production system off to save it so that we can rerun the entire system for a week's worth of stuff. And then once it has tested and worked over that week, we use that proxy that's splitting all the incoming requests to actually set up the new system and run it, but on duplicate computers so that you can actually run it and see the results of what it's doing over time on the real incoming data to prevent this kind of a thing. But that means you have to double your hardware plus some to do the proxy in between. And that's expensive. So, there are the risks that you get it wrong and the expense of doing it right, which can be quite large. Alrighty, this is our last week. I think every one of you have done just spectacularly through this whole upset in our entire processing and lives. So I wanted to tell you I appreciate that very much. And I have tried to also do a good job, although some days, I think it does work and some days I think it doesn't. But I'm appreciative of every student in this class very much. We have one more regular lecture, and that's Wednesday, which I'm going to finish up the process of distributed signing. And then Friday, I'm going to have a little bit of a review session for what's on the final. I have not written the final yet. I wouldn't get bent out of shape about what's on the final. It's probably going to be pretty straightforward and pretty easy. And we will have a little bit of a review of what we're going to cover on the final, and I'll have some sort of a plan for what we're going to do for the final. It will be a take-home final, so you will have time to oh no, he didn't cover this material. You can actually just send me an email and we will work out what it is. I'm not opposed to answering questions about it either, because I wrote a bad question on the final and it doesn't make any sense. Always a possibility. Or the flip side is, as in, where is the information on this and what are you expecting? Or just, questions about how it's all supposed to come together. Alrighty, that's it for today.